pick up where we left off last time. If you remember, we were doing the analysis of discrete time systems in the time domain. And the last time we looked at the response of the system to zero input conditions and non-zero initial conditions. Now we need to determine the response of the system to a non-zero input, right? If you drive the system with something that's non-zero, and then we're going to get the total response as the sum of the zero input and zero state. So if we follow our lessons learned from continuous system, then we know that what we really need to determine is the impulse response. Because once we know the impulse response, then I can determine the response of the system to any input by convolving the input to the impulse response of the system. So let's talk about unit impulse response. So consider nth order differential equation. That describes our discrete time linear system. So we write those as e to the n plus a1 e to the n minus 1 minus 1 all the way plus again operating on your output is going to be equal to v0 e to the n plus v1 e to the n minus 1 all the way to the n operating on your xn. In the shorthand notation, we call this q of d operating on y of n is the same as p of e operating on x of n. The response of this system has a general format where the output is going to be your y0 input of n plus y0 state of n. Zero input is the response of the system to the initial conditions. If the system is not relaxed at the time or the sample n equals 0, then it will respond with this part. Zero state is the response to the input, assuming that the the initial conditions were all 0, meaning that the system was relaxed. And then because the system is linear, the superposition holds, so the response in the most general case is going to be a combination of the two. To obtain the zero state response, I guess the straightforward way would be to first obtain the impulse response of the system. The impulse response in the case of a discrete time system can be determined two ways. One is through direct evaluation of your difference equation. There is nothing here that prevents me from substituting delta of n here instead of x of n, and then just evaluating, what the output is going to be. That's called direct evaluation of your impulse response. This one has good sides that it always works. It's very simple. You just have to be patient and calculate. But the downside of it is it doesn't provide us any additional insight into the behavior of the system. So to correct for this downside, we're going to actually derive the closed form for the impulse response, how it is similar to the one that we have for the continuous system. So where we can derive the form or derive the impulse response of the linear system directly from the difference equations. So let me just summarize what I just said. So two ways of determining impulse response. The first one is direct evaluation or iterative evaluation of the difference equation, this guy here. And the second one is closed form solution. So let's just illustrate iterative evaluation. There's really nothing much to teach there, but one example would be good to go through so that you get a feel about what does it take. So iterative evaluation. We start saying Q of E applied to Y of N is going to be equal to P of E applied to X of N. But if I make X of N equal to delta of N, meaning that my input is essentially delta, then my output is going to be your impulse response. And I have this equation here, Q of E, H of N is equal to P of E times delta of N. Now this one will have, because the polynomials are of the order N, will have N coefficients or N values for H of N that needs to be determined. And we'll have to at least N values. And we'll have to run this through more than N iterations. But also what we know to start the recursion is H of N is equal to 0 for every N smaller than 0, right? Subject to these initial conditions. So let's look at an example here. Let's consider a system that is given by the following differential equation. Y of N minus 0.6, Y of N minus 1, minus 0.16, Y of N minus 2 is equal to 5 times X of N. This is the same system that we analyzed the last time, looking for its natural response, to its zero input response. Now, how do we evaluate this how do we look for impulse response here? Well, first of all, X of N needs to become delta N, and then what I'll do is I'll move all the other terms to the right-hand side. So I have H of N has to be equal to 0.6 H of N minus 1 plus 0.16 H of N minus 2 and plus 5 delta of N. So that's the same equation just rewritten. Instead of X of N, I have delta of N because my input is now delta. And I'm taking the terms for Y that are on the left-hand side and I move them to the right-hand side so that I get the value of the impulse response to the given sample N as a function of the input and the previous values of your impulse response. Now, what I do is I just patiently read through samples. So 3, 4, 5, 6, and so on. So this is your delta of N, your input. This is H of N minus 1. This is H of N minus 2. And this is H of N. So how does my delta look like? Well, it's 1 and N equals 0. And it's 0 for all the other lines. So this is my input here. I have initial conditions that the system was relaxed before I hit it with delta. Therefore, the outputs are equal to 0 at the point where n equals 0. So, meaning that age of minus 1 is equal to 0, age of minus 2 is equal to 0. Before I actually presented delta, the system was relaxed. Now, age of 0, from here, I can calculate what age of n is going to be when n is equal to 0. It's going to be 0.6 times this one, 0.16 times this one, plus 5 times this guy. So it ends up being 5. Now the clock ticks, this becomes 1. Now this is age of 0, which is this guy here, so this becomes 5. This value here becomes whatever was here. And now I can calculate this value. And then this value is going to be 5 times 0.6, which is 3, and plus 0 plus 0. So this is just 3. And then you do it a couple more times. So let's say this is now the value of this guy. So this becomes 3. Then 5 moves over here. And then I can calculate the value of the output as 0.6 times this plus 0.16 times 5. And when you do that, this is 2.6 and so on, right? You can see how this works. You just have to be patient and go through these evaluations one by one. What comes out here is your age of n. And you get age of n in terms of, in terms of real numbers or in terms of the actual numbers. But the problem with this, as I said earlier, there's no insight that you get into these numbers. There is no understanding of whether there's what are the natural modes and what is actually the build-out of this impulse response. That insight we're going to get from the closed form. So let's look at the closed form of the impulse response. Here's what we know about the impulse response. It will have, or may or may not have a delta pulse in it, depending on whether there's a direct coupling between your input and the output. Here was an example where there was a direct coupling. You can see that y of n is some function of x of n. So the x of n is led directly to the output. Therefore, we had the impulse right in the first output here, and then it's going to consist of this term, and then it's going to have your natural modes here that are starting with u of n. Because once the impulse is presented to the system, it disappears, and then you can think of that system as being initialized with some initial conditions that is left on its own to go back to the 0 input, right? And then what happens to that system, it actually behaves as if it is a 0 input system with some non-zero initial conditions. And we know that the response of that kind of system is going to consist of the natural modes. So your every impulse response will consist of the two parts. It's going to have this impulsive part that may or may not be there, depending on whether there's a coupling between input and the output. And this part here, that is going to consist of a natural mode. Now, if I take this equation here, and I substitute that into the original, difference equation, this guy here, here's what we get. So substitution of plus into, the derivation of this is very similar. We went through the derivation of this in the case of a continuous system. Remember, we defined a companion system and went through the whole thing. I'm going to give you a shortened version here. There's no need to repeat that. And you will see that the result is almost identical to the one we obtained there. So substitution of this into the start gives me the following equation. Q of E, now applied to my to my impulse response, which is this thing here, A0 delta of n plus yc n times u of n. This u of n is the step function that turns off this one for n being smaller than 0. Needs to be equal to p of b. Now applied to my input, which is in this case delta of n. So what did I do here? I just took the form of my impulse response, put that as the output y, and then my input is an impulse. So impulse will generate this kind of impulse response. What I don't know here are two sets of things. One is I don't know the value of A0. I would like to be able to determine that straight from the difference equation. And this yc of n will consist of n modes, right? Where the n is the order of the difference equation. Every one of these modes will come up with an undetermined coefficient that I would have to provide the initial conditions for, right? So I have essentially n plus 1 things to solve. I need to solve for A0 and n coefficients of these natural modes that will build up my impulse response. But expanding on this, let's first look at, I have Q of E, and I can take this A0 here, apply to delta of n, plus Q of E, apply to yc of n, times u of n, has to be equal to P of E, applied to delta of n. Now, these natural modes are solutions to my difference equation. Because I'm applying Q of E to them, remember these guys came out of the solution to Q of E applied to this equals to 0. Therefore, this part here is equal to what? Right? Is equal to 0. So this part here is equal to 0. And then I have the equation that says that A0 applied to let me just write it first the shorthand, Q of E applied to delta of n has to be equal to P of E applied to delta of n. Why can't you just cancel it? Can we do that? Can we cancel delta of n on both sides?
Then we won't have any equation.
Yeah, but that's not the reason. We wouldn't have any equation. No. We wouldn't have any equation if I just erase this too, right? But it makes no sense to do that. Remember, this is not multiplication here, although we write it as a multiplication. This is an operator. So this would be like dx over dt on one side and dy on dt on the other side, and I cancel d over dt. And I say x is equal to 1, which is not the case, right? So let's expand this to be more clear what it means. This means that A0, now when this Q of E, and I have it spelled out over there, you can see this is e to the n. So I can say that on the left-hand side, I have delta n plus n, because that e to the n advances my delta by n, plus A1, delta of n plus n minus 1, plus and so on, plus an delta of n has to be equal to B0 delta of n plus n plus and so on Bn delta of n. Keep on mixing between these square brackets and brackets. Okay, so let's work on this equation here. This equation has to be true for every n. So if you look at now what delta means, really the only terms that survive are, let me just write it slightly different and then we'll see. Let's say set n equal to 0, gives me something like this. A0 delta of n plus delta of capital N minus 1 plus and so on. Oh, I forgot the third here. Plus A1 delta n minus 1 and plus an delta of 0 has to be equal to b0 delta of n plus b1 delta n minus 1 and plus and so on plus bn delta of 0. Okay, that's what needs to happen. I think I've probably made my mistake here, right? It should be like this. Now, if you equate this term by term, delta of capital N is equal to 0, right? All of these terms are equal to 0 except this one here. So we end up with equation A0, AN has to be equal to BN, and therefore your A0 has to be equal to BN over N. So, therefore, our impulse response, H of n, has to have a form of Bn over An, delta of n, and then plus this Yc of n times U of n. So that's the form of our impulse response. We solve the value of this coefficient here that gives us the value of the pulse in the impulse response, but we still have n coefficients to solve in this case, right? We have still n constants here, that each one associated with one of the natural modes of your this part of the impulse response. We're going to solve them by introducing n initial conditions that will come from iterative evaluation of the H of n. So since we have a differential equation, we can determine the first n values for H of n and then substitute in here. So the initial conditions used for determining the constants multiplying natural modes in Yc of n are determined through iterative evaluation of H of n. In other words, you're going to determine H of 0, H of 1, H of, as many as you need to determine the constants of this mode here. So let me go through a simple example here that illustrates this process. So that's example 3.12 in the text. Consider the system given by difference equations. So we have y of n minus 0.6 y of n minus 1 minus 0.16 y of n minus 2 is equal 5 times x of n. So no, that's the same system as the one I had on this side of the board. I regret the fact that I didn't take it all the way through, but maybe I'm not going to need all of these H of n's. Actually, I'm not going to need but 2 of them. So here's how we approach this. We have several steps. Step 1, we actually need to determine the natural modes so that we know what makes this guy, right? What are the modes that, what's the format of this YC of n? To do that, we form a characteristic equation here. So Q of lambda is going to be lambda squared minus 0.6 lambda minus 0.16, and we're going to equate that to 0. How did I form the characteristic equation? Straight here from the difference equation, where I look at the highest. This goes with the second, third, and then 0th over here. Now we solve this for roots, and this is going to be 0.6 plus minus square root of 0.36 plus 0.64 over 2. So I get lambda 1 equal to 0.8, and lambda 2 is equal to minus 0.2. So those are my two roots of the characteristic equation. And at this point, I can write the full format of my impulse response. I know that the impulse response is in the form of Bn over An times delta of n plus Yc of n times U of n. This U of n is the step function. Since Bn in this case, and what is the Bn? Bn would be the multiplier B that is along the same order as this one here. So in this case, it would be the one delayed by 2. So in this case, Bn is equal to 0. And I have that my impulse response consists only of natural modes. So my step 3, I can write my impulse response as consisting only of the natural modes. So H of n is going to be C1 times the first root, which is minus 0.2 to the n, plus C2 second root, which is 0.8 to the n, everything multiplying U of n. So that's my form of the impulse response. I have two constants, C1 and C2, that I need to determine somehow. By looking at, since this is the same system for which I did the iterative evaluation, I have the values at age of 0 and age of 1. So for n equals 0, I get C1 plus C2 are equal to 5. And for n equal to 1, I get minus 0.2 C1 plus 0.8 C2 is equal to 3. That's coming from these two numbers, 5 and 3. This is exactly the same example. So now by solving for C1 and C2, one gets C1 equal to 1 and C2 equal to 4. And finally, I can write my H of n as C1, which is minus 0.2 to the n plus 4 times 0.8 to the n multiplying U n. Final test is, let's check if this works. If I put n equals 0, this is 0.2 to 0 is 1. 4 times 1 is 4, plus 1 is 5. So that's that 5 over there. When n is equal to 1, this becomes 4 times 0.8 minus 0.2. 4 times 0.8 is 3.2, minus 0.2 is 3. And you can see that it kind of matches that response over here. Now, this one gives us the right numbers, as I said, but there's no insight. This one actually tells us, you know, and helps us easily predict the value of this impulse response for any arbitrary n. Okay, so let me go through a couple of other examples. This is your exercise 314. I solved just A and D because I found those two. If you're interested, there is probably B and C as well. So let's just go through a couple of more examples illustrating the technique behind this. So this is exercise 314. Here we have a system that has y of n plus 1 minus y of n is equal to x of n. Okay? So what is the n in this case? Capital N. Capital N is equal to 1. So this is the first order difference equation. And let's just apply these three steps that I have here. In step 1, we're going to write the characteristic equation and solve it. Characteristic equation here is Q of lambda equal lambda minus 1 is equal to 0. We get a solution lambda equal to 1 as a solution to this thing. So now we get y, okay, so yc of n, which is now formed as just characteristic modes here, becomes lambda n times u of n, or essentially just I don't have to put lambda, I will put it later, but it becomes 1 to the n, which is just 1. Right, so this is your natural part of the impulse response. Step 2, I'm going to write out the impulse response. H of n is going to be Vn over An times delta of n plus yc of n times u of n. Now in this case, observe that your Vn is the coefficient here is equal to 1. Your An is minus 1, right? So Vn over An becomes minus delta of n, and then plus u of n. So that's I forgot to say that this can be anything times this, right? So I can have any constant here that multiplies this u of n. And then step 3, I need one initial condition to solve for this constant c. Now, how am I going to determine that initial condition? If I substitute here delta of n, then this becomes my difference equation that allows me to solve it. So if I rewrite this slightly, I can say something like this. H of n plus 1 is equal to H of n plus x of n. Or I can say, if I shift this to by 1, I can say H of n is equal to H of n minus 1 plus delta of n minus 1. Now if my, instead of having here H, I need to do delta, because H is the response to input equal to delta. Now if I look at this equation here, and I solve my H of 0, so n is equal to 0, H of 0 is going to be H of minus 1 plus delta of minus 1. So what's the value of delta at minus 1?
0.
0, and the system was relaxed before delta. So h of 0 has to be equal to 0. So now that I know that, I can look at this equation here. I have h of 0 is equal to delta of n minus c u of n. But because of this condition here, I know that this has to be equal to 0. So what's the value of c?
1.
C has to be equal to 1. So your h of n, I should, 0, 0. So h of n is going to be equal to delta of n minus u of n. And if you think about what this is, let's just draw it. This is n. This is delta of n. So this is how delta of n looks like. And u of n looks like this. So if I put a minus, oh, but let me, oh, I messed up, right? So there was a minus here, right? So there's a minus here, and then C needs to be equal to minus 1, right? So this is minus plus, okay. There we go. So this is minus delta of n, looks like this. And this is u of n. So if you add the two, what do you end up with? These two first samples cancel, and then you just have these guys starting from 1. Right?
U of n minus 1.
So this is equivalent as u n minus 1. Now that's just a little bit fancy work. So this is u of n minus 1. This is a little bit simplified, but this is fine too. You know, if you just leave it like this, it's fine as well. Right? It's easy to understand how this simplifies into this, but this is also a valid form of the impulse response. That, as a matter of fact, this one is more instructive because it tells me two things. It tells me that your AN is different than 0, and BN are different than 0. Therefore, you know, you have them here, and then this is a natural response. It tells me what lambda is as well. This one is a little bit, all of that combined, so it's not clear. The two are not separated in this final expression. Okay, so that's the second example. Let's take a look at one more example that's also instructive. So although I gave you this formula, general form or closed form solution, there is a weak point here. And weak point is if AN is equal to 0, then you cannot determine this coefficient here. Right? So this format is only applicable to the cases where AN is different than 0. In other words, to look at this equation here, this guy here needs to be different than 0 for this to even be applicable, so that you can use that. So let's take a look at an example where that's not the case. So that's an example D, where here the difference equation is yn equals to 2x of n minus 2x of n minus 1. Now, I guess we can So here, you can say that this is y of n minus, or rather plus, 0 times y n minus 1 is equal to 2 times x of n minus 2 times x of n minus 1. This part here is your an, and this is equal to 0. So the closed form formula cannot be used. But that's nothing nothing extraordinary. You can always, use the direct method for evaluation. So here, direct method it says that your age of n is going to be equal to 2 times delta of n minus 2 times delta n minus 1. And we just easily say, for example, age of 0 is going to be 2 times delta of 0 minus 2 times delta of minus 1. What is the value? 2. Age of 1 is going to be 2 times delta of 1 minus 2 times delta of 0. What's the value here? Minus 2. And age of, for example, 2 becomes 2 times delta of 2 minus 2 times delta of 1 is equal to 0, and it's 0 after that. So it's very easy to determine this by just evaluating through the recursive equation. Right? There's no problem there. Okay, any questions here? So where do we stand now? We know two things. First thing is we know how to determine the natural response, right? The response of the system to 0 input. If we have initial conditions, we solve the characteristic equation, you write out the format of the natural response, and then solve the coefficients by applying the initial conditions. Through what we covered so far today, we know how to determine impulse response. And now the question is, how do I determine the response of the system to an arbitrary input? So system response to arbitrary inputs. So here's a picture of x of n, and it's here it is even more evident than in the case of a continuous system. But let's just write this out. So this is 1, 2, 3, 4, 5 minus 1, and this is your x of n, having all of these values at different points. I can see this as a signal x of n. Or I can straight from this graph here write that x of n is going to be sum when m goes from minus infinity plus infinity, x of m times delta n minus m, right? In other words, I'm seeing this x of m as a whole bunch of deltas, right? The delta is multiplied by the value at x of m, and it's centered at the point n minus m. Right, so I see this x of n is this plus this plus this plus this plus each one of these individual impulses. The value of this impulse here is x of 2 times delta of n minus 2, right? So if I substitute n equal 2, I'm going to get this value. If n is different than 2, then I get value somewhere else, right? So this particular thing is x of 2 delta. This here is x of 3 delta of n minus 3, and so on, right? And then I get the entire x of n as sum of across all m's. So what I'm doing here is I'm decomposing my input as a whole bunch of impulses, right? Which is very much the same thing as we did in the case of the analog. Now consider now my discrete time system. Linear system here, for which I know this. If I present delta of n, what is happening at the output? H of n. And this is my linear time invariant discrete time system. So now, if I present my input, I see input as a whole bunch of deltas, then every one of these deltas will produce what? Would produce H, right? Whenever I see delta at the input, what will happen at the output, there will be an impulse response, right? So if I have decomposed my input as a whole bunch of delta functions, my output needs to be linear sum of delta responses, of impulse responses. So now if here is x of n, I can directly write what y of n has to be. Y of n has to be sum across all impulse responses. So n goes from minus infinity to plus infinity. X of n is a magnitude of the impulse, and then impulse response is this. Right. And then we recognize this, it's a good friend of ours. This is what we call convolution in a discrete time domain. And the shorthand notation for this would be x of n convolved with h of n. And we discover once again that if I know the impulse response of the linear system in a discrete time or continuous time, that's all I need to know to be able to compute the output. Because if I know the impulse response, then the output is going to be convolution between whatever comes at the input and the impulse response of the system. And the convolution here is, since we're in the discrete time, it's not going to be an integral, but it's going to be a sum of very similar shape to the convolution integral that we dealt with in the continuous time domain. Now this convolution here has some very cool properties that are very analogous to the properties that the convolution in time domain has. But nevertheless, let's just state them and see if there's any things that are slightly different than what we encountered in a time domain. So some properties of convolution of sum. You know, what we had in a discrete time, in a continuous time domain, was a convolution integral. This is a convolutional sum. Both of them, shorthand, we can just call convolution, right? If we know what the convolutions are, of. So first one is commutative property. And this one says is x1 of n convolved with x2 of n is the same as x2 of n convolved with x1 of n. The second one is distributive property. That says that x1 of n convolved with x2 of n plus x3 of n is the same as x1 of n convolved with x2 of n plus x1 of n convolved with x3 of n. Both of these properties just come from a linear nature of the sum, right? The sum has these properties, so it kind of convolution inherits that from the sum. And then the third one is associative property. This one says if x1 of n convolved with x2 of n, that is prior to this convolution convolved with x3 of n, well, I can just associate and first convolve x1 with x2 and then convolve the result with x3. So this is x1 of n convolved with x2 of n, and then convolve the result with x3 of n. All of these properties are going to be essential to us to understand what happens if you start combining systems, right? If, for example, let's see this one here. If I cascade systems, right, then the output of the first one is cascaded, it serves as an input to the second one. So if you look at, then to obtain the overall response, you would have to take the input convolved with the impulse response of the first one, and then convolve that with the impulse response of the second. Well, we can approach it differently. We can understand these two systems in cascade being one system, they just put that in one box, whose impulse response is the convolution of the impulse responses of the individual ones. And then we can treat the whole thing as one system to which we present it. Those kind of considerations we're going to be, for these kind of considerations, we're going to be using these properties. Fourth is shifting property. This one says if x1 of n convolved with x2 of n produces c of n, then if I delay either one of them or both, x1 of n minus m convolved with x2 of n minus p is going to result c of n minus m minus p. Let's say p is equal to 0, then I'm just delaying the first one, then the output is delayed by the same amount to which I've delayed the first one. Likewise, if m is equal to 0, and I'm just delaying the second one, then the output is delayed by just the amount of the second one. If I delay both, then the total delay is going to be sum of the delays between the first one and the second one. That's an important property for us. Another interesting property is convolution with an impulse. X of n convolved with delta of n gives me back x of n. How do I understand this? Right? In a lot of applications that we, let's say, have in communication systems, we are running the signal and we would like the end-to-end of the system to behave as if it's an ideal filter, meaning that it lets the signal go through without any changes to it. What does ideal filter impulse response look like? Well, we can think about it. Okay, if I feed an impulse, what do I get at the output? If I have an ideal filter that just lets the signal go through, and I put in an impulse, what is it that I'm getting at the output? Getting my impulse back. In general, we allow scaling and delay, but the thing is, you're getting your impulse back. So the filter that has impulse response equal to an impulse is an ideal filter. And if you feed this filter with an arbitrary input, you're going to get your input back. Right? That's one way of interpreting this equation. The other way is what I have here. If you look at what this is, it is essentially x of n convolved with delta of n. And we see that right away from this equation that that's the case, right? So this is yet another way to see it. You can see input as a whole bunch of impulses put together, or you can see an input as a response of an ideal filter to your input, right? Where every impulse creates an impulse back, right? So therefore, you know, the convolution of x of n and an impulse is your signal back. Now, equation that I have here is valid in every case, meaning that your x of n and h of n can start and end in arbitrary position along the sample axis. Usually, in a lot of applications, we deal with the causal systems. So if the system is causal, then this the convolution gets a little bit simple form. So for causal systems and causal input signals, so you have your y of n is again x of n convolved with h of n, which I can write as a sum when, let me just start here, m, and then I can say h, x of m, h of n minus m. But because the input is causal, is there any need to go in this sum before 0? No, because x for m smaller than 0 is equal to 0. The input is causal. So I'm going to be summing here from 0. Because the system is causal, its impulse response for negative samples is 0. So is there any reason why should I go in this sum beyond m equal to n? No. So when this ends up being simplified, and your y of n is just x of m, m goes from 0 to n, x of m, h of n minus n. So that's how we can evaluate the convolution for between the causal input and causal impulse response. So let's do one example here, kind of illustrate calculation of this sum. Again, the sum can be evaluated by doing shifting and flipping and all of that. But before you do any of these things, my suggestion is always plug it in and then see if you can solve this analytically. There's nothing that is really shifting and flipping. It's just the way how we can evaluate this graphically, right? So let's just look at an example and see if we can, evaluate the convolution directly just by using the summations. So this is example 313. So I have my input signal x of n equal to 0. Or one signal equal to 0.n. And then my second signal y of n is equal to 0.3 n u of n. And the question is determine x of n convolved with y of n. That's what we need to do. So let me define signal c of n, which is x of n convolved with y of n. And let me just write out the expression of what does this mean. This means I need to sum when m goes from minus infinity to plus infinity, x of m times y of n minus m. This is what I need to do. So let's substitute now what these signals are. So I'm still leaving n goes from minus infinity to plus infinity. But instead of x of m, I can write this. So this is 0.8 to the power of m times u of the power of u of m. So this is my first signal. Use the parentheses. And then times, the second signal is going to be 0.3 n minus m times u of n minus n. And now I use the fact that both of these are causal. So I look at this u of m and realize that it kills pretty much everything for m negative. So I can say that this is sum when m goes from 0, and then this one becomes 1, right, for all other m's. So I have 0.8 to the power of n, 0.3 n minus m. And I realize that this one here becomes equal to 0 whenever n is exceeding n. So all I need to do is sum this up to n. Right? This becomes relatively easy. 0.3 to the n goes outside, so I get 0.3 to the n. And then I get sum when m goes from 0 to capital N, 0.8 over 0.3 to the power of n. Okay? Now let me expand this a little bit so that we understand what this entails. This is 0.3 to the power of m. 1 plus 0.8 over 0.3 plus 0.8 over 0.3 squared plus and so on, plus 0.8 over 0.3 to the n. When it comes to doing all of these summations, there are two general results that you should know. So let me put them here. First one is what I call here Sn. And this is 1 plus a squared plus and so on, plus a to the n. This summation here is equal to 1 minus a to the n plus 1 over 1 minus a. And it's true, valid for any a, right? Different than 1, right? But in the case when a is equal to 1, it's trivial, right? It's just equal to n. But there are no restrictions on the magnitude of a. This always converges. Why does it always converge? Because it's finite, right? You're summing n finite n numbers, so even if they're huge, it's just going to be n times huge. It's not going to be infinite. The second one, general result is S infinity. Well, now it becomes tricky because there is no n here. You're summing, this is not n numbers, this is a series. And the general result here is this is equal to 1 minus a, but under condition that a is strictly smaller than 1 in magnitude. If a is larger than 1 in magnitude, then this may not converge. Actually, almost always it's not going to converge. So, so you cannot sum any of these. Here, a is larger than 1, but there's only n of them to sum. So we can do that easily. So C of n becomes 0.3 to the n, and then I have 1 minus 0.8 over 0.3 to the n plus 1, 0.8 over 0.3 to the n plus 1 over 1 minus 0.8 over 0.3. So this can be cleaned up a little bit. I'm going to multiply everything with 0.3 to the power n plus 1. And if I do that, then I end up with 0.3 n plus 1 minus 0.8 n plus 1. And then downstairs I have 0.3 minus 0.8. And then really, if you type this up a little bit, 0.8 n plus 1 minus 0.3 n plus 1 over 0.5. So that's the convolution of these two signals. Of course, this is valid for n greater than 0. Why? Because the two of the signals are
Causal system? Is it because
yeah,
of
the
the
two of the signals are causal, therefore your response needs to be causal. You have to be careful, because if I look at this here, without this, it would appear that it's valid for every n. Right? So the proper way to write this final result would be C of n is equal to 0.8 n plus 1 minus 0.3 n plus 1 over 0.5 times u of n. And then it's clear that this is only valid for n greater than 0. Now in your textbook, there are a lot of these two results you should keep handy. If you do problems, you're going to memorize them anyway, so you might as well memorize them right away. So it reduces the trouble when you're doing the problems, but they're also very useful. They appear all the time. Right? So it's good to know them. And your textbook gives you a whole bunch of examples of the convolution that will help you, evaluate specific cases. But a lot of times, this is all you need, right? Definition and what does it mean when it's say convolution of the two sequences, and then from this point it's just a map to get to the final solution. Just final remark here, although we're not specifically concerned with the complex sequences. At every one of these lectures at the very end, I kind of give you what happens when the sequences are complex. So I just put that in here for the sake of completeness. Response to complex inputs. If you're in communication, then complex comes as a second nature to you, because we have two components that are being processed in parallel. And some of you went through advanced filtering class. We had complex signals all the way through. But in general case, your input consists in two sequences. One is we call real, and the other one is your imaginary sequence. And your impulse response is also going to be complex. It's going to have two parts, real and imaginary. And then your output sequence is going to be convolution of your input and your impulse response, which when I substitute that, it becomes x real of n plus j x imaginary of n. Everything convolved with h real of n plus j x, h imaginary of n. And then you can see here what happens is, instead of doing one convolution, you end up doing four of them. So you end up xr of n convolved with hr of n minus xi of n convolved with hi of n, and then plus j xi of n convolved with hr of n, and then plus xr of n convolved with I goes with r, and then r goes with I. So nothing fancy, just remember that if you have a complex convolution, that actually ends up giving you four convolutions that you need to resolve. Just like if you have a complex multiplication, it actually is four real multiplications, right, that you need to do in your computing hardware. Okay, so let's look at some problems that exercise this material. Well, problems are 3.7-1, -2, -4, and then 3.8-1, -2, -3, -4, -5, and -7. Okay? Any questions?
No lecture next?
Correct. On Thursday, there will be no lecture. And then when we come back on next Tuesday, we have one more lecture, and then next Thursday is a review session. So it would be really helpful if you just use these few days to solve all the problems, and then, let's have a lot of questions for that review section next Thursday. Am I right, or?
Right.
Am I, okay.
We are getting really